things going. All right, so yes, your compliment set is due Thursday. There are office hours with the TA on Thursday morning, so when you have your last minute panic, you know who to call. The answer is not me. Right. Okay, yeah.
Is problem set 3 also going to be a mini one to sort of compensate?
No.
No.
It'll be a 2-week assignment. It'll be a 2-week assignment. This was just to get us a little bit, well, there are things I want you guys to think about, but also in terms of where we are in the lectures, kind of back on track. I hope. All right, so let's see. Last time we were talking about the production of squeezed light, and that the way one makes squeezed light typically is through the process of parametric amplification. And parametric amplification, it can be seen, for example, in 3-wave mixing. You can also have it in 4-wave mixing and other things, but anyway, I'll just talk about it in this context. And so in 3-wave mixing, there are 3 waves. Typically, they're called the pump, the signal, and the idler. And the process has different conditions for this to be effective coupling of these 3 waves. So we're choosing the pump frequency to be equal to the sum of the signal and idler frequencies. And the wave vectors add up. Okay. Of course, the wave number depends on the index of refraction as well as the frequency. So what we showed is that the wave equation that follows from Maxwell's equation are these nonlinear differential equations, okay? And they couple together the amplitudes of the signal, the idler, and the pump. And under the condition that we're thinking about this from the point of view of what's called parametric down conversion, or parametric amplification, where we have a very, very strong, intense pump beam. And this process is a weak process. This process by which we generate this current that radiates these other fields is a weak coupling, which typically it is. We wish it were higher, but it's typically not very efficient. Then we can make what's called the non-depleted pump approximation and ignore any of the energy that is depleted from the pump in the process of radiating these other fields. In which case, we get these linear set of ODEs that couple together the signal and idler together, okay? In this way, where this guy's coupled to the complex conjugate. So these equations lead to parametric amplification of the signal and also the generation of a down-converted. So this new wave that's oscillating at the idler frequency has a lower frequency than the pump. So that's why it's called down conversion. I'm converting it to a lower frequency. Okay, so I've also generated this other wave. Okay? In the particular case that I just wanted to talk about, this specific case, that we had degenerate signal and idler. So I choose that the pump is equal to twice the frequency of the signal, where the signal is half the frequency of the pump, and they're lined up so that we phase match, okay? So they're collinear, and the sum of the wave vectors add up in this way. Then this equation becomes one equation where the amplitude couples to its complex conjugate. Okay, and that's an equation we can solve, and we have solved. And the solution to this equation is this, where this has some magnitude and some phase, and the phase here is related to this phase through some minus signs and odds, and you're figuring that out for homework. Okay. This is a Bogoliubov transformation. Okay. And what we know in that situation is that we have phase sensitive amplification. Actually, but use this board here. That is to say, the component of the signal along that quadrature is amplified. Along that quadrature, the quadrature. And this thing, of course, this phase here is equal to, is related to, is a function of the phase of the pump. Because this kappa parameter here is proportional to the amplitude of the pump. And that pump has a magnitude and a phase. So the phase along which I amplify is dependent upon the phase of the pump. Yes?
Why is there subscripts on the Z's for the...
Because there are three different directions.
Oh, I see.
Z of the pump, Z of the idler. So we're looking at one-dimensional. It's a complicated story when they're not along the same direction of then how do I decouple these equations? But when they're all along the same direction, I can solve it more easily. Otherwise, I have to think about whether rates. In this case, they're all along the same direction, so there's only one Z direction. Right? That's why I made this point of being collinear.
Okay.
Otherwise, it's complicated, and I don't want to get into it. You have to think about where the rays intersect. It's a piece of geometry, and it's not really so important. Okay, but the thing that I did want to say here to remind us is that, you know, the other quadrature is de-amplified. So we have a, yes?
Can you just push the top word up?
Certainly. Sorry. Right, so if I were to think about the phase plane in terms of the x and p quadratures of this guy, then if I have some signal that has some phase relative to this quadrature, then what this process does is the component, say, along P, oh no, the way I've written it, this guy is de-amplified and this guy by this minus sign over here. So the P quadrature is amplified and the X quadrature is de-amplified. So after the fact, if this was the input signal, the output signal would look like that. Okay, one quadrature would be amplified and the other quadrature would be de-amplified.
These are quadratures that are shared between the two signals?
There's one signal. I have two copies of it, but there's only one. This is the degenerate case where the signal and either are the same, so that these guys add up together. I'm trying to understand your question.
It's not, you're drawing two arrows there, but when I think of a quadrature, I generally think of the quadrature of a signal.
It is. I'm sorry. This is the input and this is the output.
Oh, I see.
I'm sorry.
No, it's,
So the input signal has a component, an X component and a Y component, or a P component, because I'm not necessarily choosing the phase. If I wanted to just amplify the signal, I would choose the phase of the pump in such a way such that it's aligned so that along the input, so that this guy was along X or P, and it would just be either amplified or de-amplified. But if it's at some arbitrary phase, then the component along X is de-amplified and the component along P is amplified. Okay, that's phase-sensitive amplification. If it was all along P, it would be totally amplified. So it's a phase-sensitive amplifier. Now, if I had a different initial case, like this, the same thing would happen, right? I mean, this guy over here would be, amplified by some amount and de-amplified by some amount and end up over here, the output for that guy, okay? And if I had some range of different initial amplitudes around this, different vectors, what's gonna happen is that range will look like this, okay? So every one of these points is mapped to one of these points, and they would be stretched out in this way because this quadrature is amplified and that quadrature is de-amplified. Okay, interesting. Of course, that is squeezing. Now I'll come back to this. I've described this completely classically. Yeah?
So the center of the distribution also moves?
It does. In this case. Now, if I started with something which was like this, then every point it would look like something like that in the end, right? Because the center has zero amplitude and it wouldn't move anywhere, right? So if I had different initial inputs that were all centered at the origin, it's the distribution, then they would move in this direction, right? Very good. Now, this is totally a classical description of three-wave mixing. Quantumly, I have some interaction Hamiltonian, which in the electric dipole approximation depends on the dipole density and the electric field. And when we have this kind of three-wave mixing process so that this polarization density depends on the products of the electric field, it's not a linear response, it's the chi2 response, then what we loosely sketched is that this goes to something that looks like the following. It has a sum over all the modes that are possibly phase matched. There's some coefficients here that depend on these guys. And then I have something, the processes which are resonant are the ones where the energies add up. And those processes where the energies add up have to do with the idea of I can have all these different amplitudes. So the point here is that the terms that are resonant, the ones that conserve energy, are the ones where the pump energy is equal to the sum of the idler and signal energies. Remember, this goes like e to the plus I omega t, this goes like e to the minus I, so these terms will be resonant, okay? On the level of the individual quanta, what this corresponds to is the situation, for example, if I look at this term, whereby I have a pump photon that comes in, it gets annihilated, and I create a pair of photons, a signal and an idler photon, in a pair creation. This term is the time reversal conjugate. It's the sum frequency where I absorb these two photons, right, and then in the process create a pump photon. Okay. So at the level of the quanta, the photons, the three-wave mixing process is a process where involving creation and annihilation of pairs of photons. Okay. And so there's an intimate relationship here between the process of parametric amplitude and squeezing and this kind of pair creation of photons, which we'll talk a lot more about. Okay, yeah?
But in reality, like when I input my beam, I only have pump photons, and that's why the rate of signal and idler creation is more.
Well, it depends. The process by which I described a parametric amplification, I put in the pump and the signal, okay? And then I'm amplifying the signal, or de-amplifying depending upon the phase that I'm looking at. If I have a non-degenerate case, I would amplify the signal and at the same time create either photons. So that would be a situation, if I thought about that process, where I send in a photon and I get more. I can think about it as a kind of stimulated amplification. But if I don't put in any pump, we'll come back to that at all, I'm sorry, if I don't put in any signal, I will still get this process through spontaneous creation of these two photons. Yes?
When we're sending over ISP there, that's IS and P, so for each of those, it's every possible mode and polarization, like every...
Yes, and the ones that dominate are the ones that are phase matched. So the only ones we ultimately put into this process that are important are the ones that satisfy these conditions, but there can be multiple ways that can happen. If I put in a particular direction either, then there might be only one. If I put in certain signals, only one either that could satisfy this. But if I don't put in the if I'm not putting any signal into this, then there could be multiple cases. Okay. Now, in the case of where we put in a strong pump into the input in the non-depleted pump approximation, then we can replace this by just the amplitude of the coherent state. Okay, that's the non-depleted pump approximation. We could just say we don't worry about any of the quantum fluctuations in the pump. It's a strong field, we replace it by its classical value. And in that case, we recognize this Hamiltonian as the one that gives rise to the two-mode squeezing.
It's the squeezing operator.
When you exponentiate it, you get the squeezing operator. So in that situation, my time evolution operator is the squeezing operator, okay? And it's gonna look something like the exponential of, some kappa involving creation and annihilation of pairs of photons, okay? That's a multi-mode squeezing, but they're they're pairwise squeezed. And the degree to which they're pairwise squeezed depends on the strength of this coefficient, okay?
Should alpha?
Kappa is some combination of C and alpha, so it depends on the amplitude of the pump. Yeah.
So did you make any assumptions about it being collinear or degenerate in the quantum case? Or
No, I did not.
Not yet.
No, I didn't make that. But let's talk about that right now, okay? So let's suppose I want to make squeezed vacuum in a single mode. Let's say it has some frequency, okay? I can do that by degenerate parametric oscillation. So I'm going to talk about, so what I have my Chi2 crystal, and I'm going to have my pump. Okay. Now, I'm not going to amplify any mean field. I want to amplify the vacuum. I want to amplify the vacuum quadratures in some direction and and squeeze them in other directions. Okay, so I'm not going to put in any field, and this is what we call spontaneous parametric down conversion. Okay. So in order to enhance the strength of this, often this is what one does is one has multiple passes of the system to build up the energy by putting it inside an optical cavity, okay? So what we're gonna do in this, we're gonna put in a cavity which is transparent at the frequency of the pump, but is going to reflect the frequency, the photons that are emitted at the signal, which is going to be at half the pump. Okay, so we're going to get down conversion, degenerate parametric down conversion at that. The way we do that is that we make this cavity resonant. I'm going to make a bow tie cavity here with two mirrors, such that the signal is resonant. So this is resonant for that. Let's just say this cavity is aligned such that at that frequency there is a standing wave mode that matches the boundary conditions, okay? And so this is going to be a strong now coupling between this mode, which has half the frequency of the pump, and the pump in this degenerate parametric conversion. And then this cavity is slightly transmitted, and what comes out of this is squeezed vacuum. This is how squeezed vacuum is made. in this kind of configuration, because it's got a cavity, it's known as an oscillator. So this is known as an optical parametric oscillator, or an OPO. And an OPO is how people make squeeze light. Yeah.
Is omega S, like what, in pump signal idler, which is omega S?
Omega S is the signal, but it's degenerate, so the signal and the idler are the same. So I've chosen them such that, remember we had over here that they add up. I've chosen the signal equal to the idler. So I've chosen the cavity to be resonant on this condition. Okay, so then there's only, in this case, the signal and the idler are the same, and that's where we get this kind of squeezing, the degenerate case that we had over here. Now the amount of squeezing you get depends on this value R, how much squeezing, how big can that be, what have people done? Often people measure squeezing in terms of how big the variance is in the quadrature. So the factor is this. Often this factor is what people quote, how big this, which is it's kind of a cheat because you squared it. It seems better that way, because you get even minus 2R, okay? Often this is written in dB, which is 10 times the log base 10 of this thing. That's how many dBs of squeezing that people always talk about. And so that's equal to, in this case, well, I'll put the minus sign because I want to know how much squeezing. This is 20 times the log base 10 of E times R, which is 8.68 times R. Okay? That's the amount of squeezing that one gets. Depends on how big R is, which of course depends on what chi2 is and the strength of the pump. And how many dBs do people get? Typically, a few dB. So, the most people get, like the record is probably 20 dB, I think, that is used in LIGO. But typically it's a few dB of squeezing that one gets in these systems. Okay, that's sort of just gives you a little sense of the numbers of this. Now, of course, I should mention one last thing here, which is that, yeah.
Simon, here, so here we are putting a pump and signal.
No signal. There's no signal at all. The signal's entering as vacuum. But I have spontaneous parametric down conversion. So from the point of view of the photons, there's a photon that comes in here that can, through this process of parametric down conversion, convert into two, can be annihilated and turn into two signal photons. These signal photons are resonant within the cavity, and you have buildup of the energy of the signal in the cavity. The pump goes right through, it's not building up. It has a single pass in this thing. But the phase matching conditions are chosen in such a way with the index of fraction such that this is a efficient conversion of energy. Okay, very good. Yeah.
So my squeezing should depend on how much energy I'm going through the.
It does, and it's here, right? So the amplitude of the pump, or the intensity of the pump, determines the strength of these coefficients. Yes.
So when people say how much squeezing we're getting, rather than talking about actually like the ratio of the two quadratures, they're talking about the value you get per R, basically?
They're talking about how much I've reduced the fluctuations relative to the vacuum. They're talking about this number. And that number in decibels is this. Does that make sense? Or telling me how much I've amplified or de-amplified the vacuum?
Yeah, I think so. It's just, here is a scaling rather than a specific number of, yeah.
Well, it is a specific number, but it's the factor by which I amplified or de-amplified. Okay, good. Now, so interesting. I mean, so one of the things, the takeaway messages from this discussion so far is, well, we have these two different pictures of how we describe squeezing. I had a completely classical description here, which led us to this picture over here. But we also had this picture in terms of photons, right? These photons that are being annihilated in this process and created. And the question then we might want to ask ourselves is squeeze light classical light? I mean, we described it there completely from classical Maxwell's equations, right? These equations of motion that I wrote down over here are the classical equations of motion of the waves. And if we had fluctuations, if we didn't know what the phasor was here, we would map its distribution in that way. In fact, this process of parametric application is exactly the one that we studied in the first problem of the first homework assignment. This is a parametric oscillator. What's going on in this process is that I'm pumping this crystal at twice the frequency of the signal, okay? And in the process, because chi2 times I have a process here that's chi2 times the pump, which is oscillating at this frequency, I'm changing the optical path length seen by the signal inside here at twice the frequency. It's equivalent to thinking about our problem that we had of a particle in a harmonic well where I'm making the well's curvature, its spring constant, go back and forth periodically at a frequency which is twice the frequency of the natural oscillation. And as you study, and I hope everyone did the problem, what you see in that process is that you get parametric amplification or de-amplification depending upon how the phase of the drive of the pump is relative to the phase of the oscillation. So if you're on a swing in the park, if you swing your feet the right way, you'll amplify. If you swing them 90 degrees out of phase, you'll de-amplify your motion. And this is exactly what this is doing. When this pump it's changing the optical path length because it's changing the index of refraction seen by the signal through the three-way mixing, and that's just doing this. It's exactly a parametric oscillator that we understood from the point of view of classical mechanics, now thought about in terms of the oscillator of the field. So now I come back to this question. Is squeezed light classical light? We have a completely classical description of it. So maybe. Meh? I don't know.
Maybe the answer was yes.
Well, why did we say it's not classical in the first place? Well, the place we said, so what we defined, one definition of classical light is it's something that is produced by classical current. And as we've discussed, if the state is produced by classical current, then it must necessarily be a statistical mixture of coherent states with some honest-to-God probability distribution. And squeezed light, the state of squeezed light cannot be expressed this way. Because if this is true, then this, for any quadrature, is always greater than equal to a half, always, if it's classical light, if it's in this definition. So from this perspective, the answer is squeezed light is not. But there's something more to it than this in thinking about how we want to think about what we mean by classical light versus not. If my state is of this form, if we have a state of the quantum field which has this form, which arises from a classical current, then this tells us something about a classical picture of photon counting. That is to say, if I have some source of light and I have some photodetectors, and that light is incident on these photodetectors, and I want to ask something about the photocurrent that is coming out of these detectors, and I want to look at some correlations between them, then what we learned last semester is that I can understand the statistics of those correlations through the Glauber theory in terms of normally ordered expectation values. So you remember, for example, if I wanted to look at I have N detectors and I wanted to look at the correlations of the photocurrent from this, the Glauber theory tells me that that is related to the normally ordered, let's say, M value of the number operator, which was alpha dagger to the M, or A to the M, right? We had that from last semester. But if I express it in this way, then this is equal to, let's just say for a single mode, just for the moment, which is a classical statistical average. So the point I want to emphasize here is when we did photon counting, if that's the measurement that we were doing, and we're looking at the photocurrent coming out of photo counting, I can understand, for classical light that is described this way, I could describe it completely the way that the radio astronomers Henbury, Brown, and Twist did in terms of random waves with some probability distribution of amplitudes, and I calculate this not from the point of view of quantum mechanics, but just statistically averaging the intensities weighted by probability. So I had a completely classical description. So when we have classical light and the measurement, emphasis on, the measurement that we're doing is photon counting, then it has a completely classical description. If it wasn't classical light and it didn't have a classical probability distribution in this representation, then I couldn't explain the photo counts I got in terms of a classical average over random weights. So for example, photon anti-bunching and sub-Poissonian statistics were examples of non-classical features. But the main point here is that what I'm talking about here is a particular kind of measurement, okay? So in contrast, suppose instead of doing photon counting, I did homodyne measurement. Okay, so I'm not going to directly photon count. I'm going to take the light and I'm going to send it into my thing, but I'm going to put in a local oscillator. And measure in the process X. Okay. And I want to know can I understand this in terms of a classical description of these quadratures? Well, if my light had this case and I wanted to say, look at, for example, let's look at the fluctuations or the expectation value of x squared. According to this, for a single mode, that would equal that, right? That's the expectation value. But this does not equal the classical expression for it. Why is that? Well, we can write it out. But the reason is that this is not normally ordered. In fact, if I look at this, x squared is a plus a dagger squared over 2, which is a squared plus a dagger squared plus a dagger a plus a dagger. And this is not a normally ordered operator. So when thinking about other measurements that I might do, other than what Glauber considered in thinking about correlations between photon counts, when I'm thinking about things like measuring a quadrature, the Glauber P representation doesn't really tell me whether I have a classical or non-classical description of the light, because the operator I'm measuring is not a normally ordered measurement. So the message here is that the Glauber Sudarshan P representation does not tell us whether quadrature measurements or homodyne measurements have a classical description. So, the moral of this story is the following, that the classical versus non-classical nature of the light shouldn't be defined solely by the source that produced the light, but also the measurement done on the light. Meaning, we just defined, we said classical light is by some definition the thing that is produced by classical current. And if it's not produced by classical current, we said it's non-classical. Well, that's true when we're looking at it from the point of photon counting. But it's not true, for example, in squeezed light, if we looked at it from the point of view of homodyne. We have a completely classical description in terms of the quadratures. And so the nature of quantumness is about what we observe, how we should describe the measurement outcomes, and can we describe those measurement outcomes in a purely classical statistical manner, and in what case are we forced into saying, no, there is no classical statistical description of the measurement. And so the measurement is critical. And the measurement that's tied to this are photon counting, which we described last semester from the Glauber theory in terms of normally ordered operators. Yeah?
So, are photon counting measurements equivalent to the information about alpha when not normally ordered? Because as far as we know, photon counting is a non-classical or non-Gaussian operation.
Yeah, we'll talk about the non-Gaussian stuff in a moment, but I don't want to get.
Yeah, all I'm trying to understand is I'm doing photon counting, but then I'm doing normally ordering, and then I'm getting alpha, which has a classical equivalent.
Right. So, according to the Glauber theory, the outcomes of this measurement that we see in photoelectric effect are given by the normally ordered expectation values. That just comes out of, thinking about how the photoelectrons are emitted in the photoionization process. And though we didn't do it very carefully last semester, we didn't postulate normally ordered expectation values. They come out. Those are the things, that's what's actually being measured in a photon counting experiment, is the normally ordered operators, okay? So if the state is of this form, then, for example, this particular M-body correlation function, M-photon correlation function, has this picture. And if it was produced by classical light, it has a completely classical description in terms of random waves, the way that Hanbury, Brown, and Twist thought about it when they thought about their correlated antennas. We don't have to think about it in terms of photons. In fact, Hanbury, Brown, and Twist did not, because they knew nothing about photons. And the physics community, well, for knowledge, how the hell can we have, this interference effect? But it was completely classical description. On the other hand, so from the point of view of this description, if I try to think about, it's a classical statistical mixture of coherent states, that's not going to give us the right description if we do homodyne measurement. If we do homodyne measurement, I can't just replace X by its classical description. These guys are not equal because X squared is not a normally ordered operator. And what it's telling us is that thinking about classical light from the point of view of this definition only makes sense if the measurement I'm doing is photon counting. But there are other measurements I can do which also have a perfectly classical description, measurements on squeezed light, as we just described. There was no quantum mechanics when I drew this. This was Maxwell's equations. And so what it's telling us is that we need a more subtle definition of classicality, not just based on how the source would produce, but how we measure it. And whether those measurement statistics, those measurement outcomes have a classical statistical description.
But if I were to measure squeeze light using the Glauber correlations, I would see that it was not, I wouldn't have any bunching.
Absolutely. So this is a sort of a subtle point, and one that's sort of related to Omar's offhanded comment about Gaussianity, which we'll get to, which is that if I had squeezed light and I didn't measure it with homodyne, but I measure it with photon counting, then those photon counting statistics cannot be predicted by a classical statistical theory, because there is no classical Glauber P representation for it. And in fact, some of the most advanced experiments that have demonstrated quantum supremacy in boson, in photon statistics have been with using squeezed light and photon counting. So that's called Gaussian boson sampling. You have a Gaussian state. We'll talk about, and keep saying Gaussian, we'll come back to that. But we're not measuring it with homodyne, we're measuring it with photons. So you're absolutely right, Ari, and that's an important point. It depends what you're measuring, whether that you see with whether there is a classical description or not. All right. So what we're interested in now, thus, is if we want to think about classical descriptions of light, what I mean by that is classical statistical descriptions of light, I want to think about some kind of probability distribution of the complex amplitudes. That's a classical description. And from the point of view of the description, from the point of view of these complex conjunctors, we think about that as a phase space representation of the state and observables. Okay. So we had one such example, the Glauber-Sudarshan. P representation. The Glauber-Sudarshan P representation is a representation of the state on phase space. And that representation for a single mode is this. So we can always attempt to express the state in this way, but that's P may or not be a classical probability distribution. If it is, then normally ordered expectation values have a classical description. But we want to think about this more generally now, how should we define a phase space representation? Okay. So I want to back up and think about phase space representations. In quantum mechanics. And this idea precedes quantum optics. what are we trying to do here? So classically, I can think about a probability distribution as a function of position and momentum. Okay? This is what's known as the Liouville theory. And in the Liouville theory, this probability distribution, I can think about this as something which is evolving in time according to the dynamics. And that dynamics is given by the Poisson bracket, something we don't teach anymore, which looks like the commutator, but it isn't. Later back at it. And then I might have some dissipation. This is classical statistical physics, where I don't know exactly the position and momentum of every particle in Avogadro's number of molecules in a gas. So instead, I think about a probability distribution evolving, and there might be Hamiltonian evolution and whatnot. And the question is, can I do this quantum mechanically? Okay. Now, this is a joint probability distribution on phase space. So this is the probability that the particle has a particular position and a particular momentum. Now we know in quantum mechanics we can't do that generally because of the fact that I can't have a state that has a definite position momentum. So I couldn't have a delta function, for example. I might ask whether I can have something that's not necessarily a delta function, but still a probability distribution. But the notion of joint probability of both x and p is fraught in quantum mechanics because x and p don't commute. So quantumly, this is a tricky business. But we want the quantum analog of this in thinking about a phase-space representation in quantum mechanics. And this was first really done by Wigner, Eugene Wigner, in trying to think about how should we define phase-space representations in quantum mechanics. So how are we going to do it? So quantumly, we have the problem that x and p don't commute. I mean, we shouldn't be able to replace quantum mechanics by this. Otherwise, quantum mechanics is classical statistical physics, which it is not. So there's something different. Or maybe there are situations under which this is a perfectly good description, because of course, classical physics works in certain approximate cases. All right? So how are we going to do it? Let's first review wave mechanics. Okay. Of course, we know I can talk about two different representations. Instead of a phase-space representation, I can think about a position representation. The position representation is one whereby I think about there's a state, and I can think about a representation of the state in the position basis. So the wave function is the position representation of the state. And the probability density of measuring x is given by psi star psi. Okay? Which of course is also equal to the trace of rho with x, where rho in this case is a pure state but this is the more general expression for this, including mixed states. Okay. So this is how I would calculate the probability, and this is an honest-to-God probability distribution, right? Similarly, I can think about the momentum representation. And I can think about the momentum space wave function. And the probability density of seeing outcome P would in this case be the square of the momentum space wave function for the trace of rho with the projector onto P. Right? Now, of course, I can go back and forth between these two representations. So we also know if I think about, if I have an eigenstate, which is, if I have a state which is itself an eigenstate of the position operator, and I ask what is the wave function associated with this, that's a delta function, Dirac delta function. And similarly, if I have a state which is a momentum eigenstate, then its momentum space wave function is a delta function in P. And we also know that I can go back and forth between position representation and momentum representation by a change of basis. And that change of basis is known as a Fourier transform. So the position representation of the momentum eigenstates are plane waves, which we take normalized in this way. Okay, and so if I were to ask about the position, how I would go between the momentum and position representation, we all know that what I do is by definition it's this, I'm going to put in a complete set of states that's my change of basis. This amplitude is e to the minus I, P over square root of 2, and that's the Fourier transform with this particular convention. And moreover, we know the relationships between plane waves and delta functions that will allow us to go between momentum eigenstates, position eigenstates, and similarly, if I, with these sign conventions that I have written, everyone with me? Okay, so that's the position and momentum representation. I should just, of course, remind us that I can also think about an operator in the position or momentum representation. So if I have, for example, the potential, which is a function of the position operator, then this has a position representation. And if I were to look at the expected value of the potential, I can think about that in terms of a classical average over x. this being the square of the wave function. It's got a perfectly classical description. And similarly, if I have the kinetic energy operator, then this thing, it has a momentum representation. And the expected value of the kinetic energy, again, has a completely classical description in terms of a probability distribution on momentum. Okay. If I think about a joint representation on both position momentum, that's where life gets complicated. Okay. So how are we going to do this? How are we going to think about a joint representation of the flavor that we see in the Liouville equation? The way we do it is through the following trick. So let me put a little aside over here. I'm going to give you a lemma. I claim that the projector onto x is equal to a delta function where the x operator is equal to that eigenvalue x. How could we show that? Well, this operator by definition can be expressed in the position basis. Okay? So this operator by definition, I can put a complete set of states. Now I'll put a dummy variable x prime over there. X is already taken, so this is, I'm getting rid of that. Sum over this. This then is an integral over x prime delta, and when this is an eigenvector of the x operator with eigenvalue x prime, everyone see that? I just replaced the operator by its eigenvalue, because when x hits the ket or the bra, it gets replaced by its eigenvalue. And now I can replace this integral is 0 unless where x prime equals x. And so this x prime is x. Okay? So, it's an interesting thing. I can express the projector onto the x eigenvector as the delta function where the x operator is equal to x. And similarly, I can write delta p hat minus p is the projector on p. Okay? So now, what I want to write down is something which is simultaneously like a projector on x and p at the same time. Now, there's lots of ways. The point is that x operator, x hat and p hat don't commute. So if I wanted to write a delta function in phase space, I have to think about the order in which I put it, because x and p don't commute. But I'm going to define what I call a symmetric delta function. Let me do before I get to that definition, I need to do a few more asides. Let's come back to this board over here. All right, so I'm going to have a classical delta function on phase space. Let's start here. So I'm going to have a two-dimensional delta function, let's say x minus x0, p minus p0. What I mean by that is just the product of these guys to one-dimensional delta functions. Now, in this case, this is classical. It doesn't matter what order. These are numbers. They commute, okay? But now I can write down what we wrote down over here in terms of delta functions somewhere. Where did we write down the delta functions? Oh, here they are. So I'm going to plug in those two definitions. It's an integral over x, an integral over p, 2 pi squared, e to the I p x minus x0 minus I x. Oh, this is a dummy x prime. P prime, x prime, p minus p0. Okay. Do you agree that this integral is a product of delta functions? Yes, right? If I integrate over x prime, I get a delta function in p. Integrate over p prime, I get a delta function in x. Okay. So now, this gives me a way of defining a symmetric delta function that doesn't depend on operator ordering. It's symmetric. So I'm going to define the quantum symmetric delta function. I'm just going to say. Let's take a look at that expression. So, firstly, all I did here is I replaced x by x hat and p by p hat in this expression. That's what I did to get from here to here. This thing is a symmetric delta function. Why is it symmetric? It's symmetric because this exponential is symmetric. Okay? Let's just look at this guy over here and write it as a power series. The first term is 1, then I get plus I p hat x hat minus x naught minus I x prime p naught. And then I'm going to get a term that's a half, and then the square of this thing. Everyone see that when I do the exponential? But when I square this out, what do I get? Well, I'm going to get minus p squared x squared minus x prime squared p hat minus p naught squared. And then I'm going to get plus I x prime p prime plus dot dot dot. When I square this out, I'm going to get x times p plus p times x. And this is symmetric in x and p. It doesn't put the x's on the left and the p's on the right. I have an equal amount. It's symmetric in x and p. Yes?
Can you also define it just as like 1/2 delta x delta p plus delta p delta x? Like something like that? Like how you do with...
Yes, and that would be the same thing.
Oh, it is the same.
It's the same thing. That's exactly the same thing. Absolutely. So, it's also an interesting fact that if I look at this guy, if I integrate out p, it's a delta function in x as expected that you would have the same thing. And similarly, if I integrate out x of the 2D symmetric delta function, I get a delta function in P. So, with that, this is not exactly what Wigner did, but ultimately it's the moral of the story. We'll talk about it much more on Thursday. We define
Why is it a integral over p on next line?
sorry, here.
Yeah.
I'm saying if I integrate out P naught, and if I did that integral, you can see what happens. I'm going to marginalize over P naught, and I have something that is only a function of x. Just as you would expect from this classical. If I integrate this over P naught, this guy this integrates to 1, I'm going to get that delta function. So, we define the Wigner function it's the overlap between rho, the state, and the symmetric delta function. Note, if I integrate this over P, I get that, which is the position space representation. And similarly, if I integrate this over x, I get, for pure state, the momentum space representation. Yeah.
So then, in the language of statistics, would it be accurate to say that, the state is to a marginal probability distribution as the Wigner function is to a joint probability distribution?
Yes, this is exactly the point. So that, let me just conclude as I was saying, you got the important punchline is that these are what we call the marginals. We know from quantum mechanics, what the probability distribution is if I were to measure x and not worrying about p. It's this. We also know the marginal, what's the probability distribution if we were to measure p alone and not x. It's that. The Wigner function is the unique function which gives us the right marginals. Okay, it gives us what we expect from quantum mechanics. Quantum mechanics gives us what the probability is of measuring x and what the measurement is. Whereas this is a joint, what we call quasi probability distribution. Why is it called quasi? Because this guy can be negative. The price we pay in quantum mechanics for the fact that there are different measurements we can do that don't commute is that we can't define a joint probability distribution for both of those. We can find a joint quasi-probability distribution which gives us the right marginals for the different observables that don't commute, as in X and P. But if we wanted to find a joint distribution, we are left with the idea of negative probability, which I think actually is extremely profound, and maybe the whole story of what quantum mechanics is trying to tell us. This operator is not a positive operator. We'll prove that. And because it's not a positive operator, this is not a POVM. Unlike position and momentum, this was an honestly not POVM. I'm integrating over projectors. These are positive operators. These delta functions are positive, X or P are positive operators, and they give us the probability of finding that. But the symmetric delta function is not a positive operator. And thus there is no joint measurement I can do that measures X and P at the same time in a precise way. And we're then forced into the idea of negative probabilities. So we're going to discuss this in much more detail, starting on Thursday. But this is the basic idea. The basic idea is that we had position representation, we had momentum representation. Those representations were defined in terms of the delta functions on X and P. They gave us the way of figuring out what the probability distribution is. If we want to write down a joint probability distribution, we define it symmetrically in X and P. That gives us the right marginals, but the fact of the matter is we can't write this generally as a positive joint probability distribution, except when we can. Because when we can, then this is classical description, and we'll come back to that. It comes back to what we mean by classical, because there are states for which the Wigner function is everywhere positive. And one such example is a squeeze state. So in that sense, the squeeze state is classical. It has a positive Wigner function. Even though its P representation is highly singular and there's no description in terms of photon counting, it's perfectly classical when thought about from the point of view of homodyne. A lot of information. We'll talk about it more next time.
When you're getting from a coherent state to
Yeah.
classical,
It is.
If you want to get from